What if I told you that one of most expensive mistakes in construction history isn't a bad design? It's what's under the building. In Mexico City, an entire cathedral sank over 9 feet into the ground, not because of bad engineering on top, but because nobody fixed the ground below. Today, we are breaking down everything you need to know about ground improvement, what it is, why it matters, and the actual techniques engineers and workers use on sites right now. Whether you are a curious beginner, a construction worker, or a civil engineering student, this is one for you. Think of it like this. Imagine you want to put a heavy couch on mattress. If the mattress is soft and saggy, the couch sinks. You would either replace the mattress or find a way to make it firmer. That's exactly what ground improvement is. Officially, it is any method that makes the soil or rock in the ground more suitable for construction, whether you are building on top of it or using it as a material itself. Engineers classify soil into three buckets: hazardous, like land near fault lines or volcanic zones, where you should simply not build. The second category is pure, like loose sands, organic soils, expansive clays, which can be treated and favorable like, and the other is favorable like compacted sandy clay mixes or shallow rock, which are ready to go. Now you might be thinking, if the soil is bad, why not just build somewhere else? Great question. There are actually four paths engineers can take when the ground is a problem. The option one is abandoning the project. Just walk away. Sounds drastic, but sometimes a site near an active fault line just isn't worth it. Option 2 is dig out and replace it. Remove the bad soil entirely and bring in good material. This used to be common, but today it's expensive, environmentally unfriendly, and slow, falling out of favor fast. Option 3 is redesign the structure. Use driven piles, drilled shafts to skip straight past the weak layer and anchor into solid ground deep down. Think of it like pushing a straw all the way through a soft cake to reach the hard plate beneath. Option 4 is fix the ground itself. This is where ground improvement techniques come in. And this is what the rest of this video is all about. The oldest trick in the book is what is called technique 1 in the types of ground improvement. That is called soil densification. This involves squeezing the air and water out of the soil so the particles pack tighter together. Think of shaking a jar of rice. At first it is loose. Shake it and it settles. Soil works the same way. This can happen shallow with rollers and compactors you see on roads, or deep underground using vibration equipment that goes 30 meters down. Technique 2 of ground improvement is using drainage and dewatering. Ralph Peck, one of the legends of geotechnical engineering, once said, "Water in the ground is the cause of most geotechnical engineering problems. Drain the water out and the soil gets stronger and lighter. This is why you see those pump tracks on waterlogged construction sites. It's not just clearing puddles, it is improving the entire bearing capacity of the ground." The third technique of ground improvement is admixture stabilization. This is basically mixing chemicals into the soil to transform it. Cement, lime, fly ash, these are the common admixtures. They chemically bind with soil particles, turning weak, unstable ground into something almost like weak concrete. Shallow mixing goes down about 60 centimeters. Deep mixing techniques can go more than 30 meters below surface. The fourth technique of ground improvement is called soil reinforcement. Here is a fun fact. Ancient Egyptians reinforced mud bricks with straw. Same principle today, just with steel bars and high-tech geosynthetic fibers instead of straw. You insert these materials into the soil to carry tensile loads, the forces trying to pull or stretch the ground apart. You will see this in retaining walls, road embankment, and slopes. The reinforcement spreads concentrated loads over a wider area, reducing settlement. The fifth technique of ground improvement is called grouting. Imagine injecting cement into sponge. Grouting fills the voids and cracks inside soil or rock by pumping in a liquid grout that hardens. It can waterproof, strengthen, and stabilize at the same time. It's often used in tunneling dam foundations under existing structures that are settling. The last technique you present is called using lightweight fields. Less obvious but super clever. Instead of the heavy soil that was there, you replace it with something much lighter, like shredded tires, expanded shell, even blocks of polystyrene foam called geofoam. Less weight pressing down means the ground below carries less load. Simple physics and big results. Okay, if you are a construction worker or you are tackling a home project that involves the ground, here is the practical takeaway. Before you pour any concrete pad, building a retaining wall, or even install fence posts, test and think about what's underneath. Waterlogged soil, soft organic spots, or expansive clay can crack your work within a year. At the small scale, the most accessible ground improvement technique are compaction. Just rent a flat compactor before you put a slab. And drainage, adding gravel subbase and perforated pipes and admixture mixing. You can buy lime or Portland cement stabilization mixes for small projects. If you are dealing with a slope that's creeping or failing, or a wet corner of your yard that never dries, those are signs you need a geotechnical engineer to look at your site before you throw money at fixes that will not hold. Alright, for the engineers in the room, let's go one level deeper. Ground improvement selection isn't just about what techniques exist, it's about matching the method to the soil type, project stage, depth of treatment, and the target property you are trying to improve. Are you reducing compressibility, increasing bearing capacity, cutting permeability, mitigating liquefaction risk? Each goal calls for a different tool. There are three stages of ground improvement relative to a project. The first one is pre-construction, the ideal window where densification, pre-consolidation, planned dewatering are most cost-effective. The second stage is on construction, where gravel columns, geosynthetics, soil nails, and lightweight fields can be integrated into the build. And the last is post-construction. This is remedial and expensive, using grouting and draining to fix problems that have already emerged. One key consideration that often gets underweighted in design, the environmental impact. Excavation and replacement. Once the default is increasingly regulated due to spoil disposal costs and carbon footprint. In situ methods like deep mixing, stone columns, and dynamic compaction are now preferred not just economically but regulatorily. Also worth flagging for students, the line between ground improvement and foundation design is blurry. When you install stone columns under raft foundation, is that ground improvement or part of the foundation system? In practice, it is both, and the coordination between the geotechnical and structural engineers on that interface is critical. So next time you walk past the construction site, look down, not up. The most important work isn't the steel going up, it's the invisible work going on below your feet. If this video helped you understand the ground a little better, drop a comment below with which technique surprised you most. I read every single one. If you are a student working on geotechnical project or worker dealing with a tricky site condition, hit subscribe. We go deep on civil engineering topics every week with zero textbook fluff. See you next time. Thank you for following.